All right, welcome to the Explainer. Today, we are going on a pretty incredible journey deep, deep inside the Earth. We're going to explore the hidden world of magma to figure out how it's born, how it changes, and how it ends up creating this amazing variety of rocks all around us. Everything from the granite in huge mountains to the volcanic rock that makes up entire islands. So let's just dive right in with a question that really gets to the heart of all this. Have you ever stopped to wonder why the volcanic rocks in Hawaii are black and create these smooth, flowing lavas, while a volcano like Mount St. Helens just erupts explosively, throwing out gray ash and much lighter-colored rock? Well, the whole secret is in the different recipes of the magma that's bubbling right beneath them. And to get to the bottom of that, we're going to follow the entire story of magma, basically in 5 key chapters. We'll start where it's born, way down in the mantle. Then we'll meet the main magma families. After that, we'll see how its chemical recipe actually changes on its journey up, explore how it finally solidifies into rock, and then we'll visit the massive geological factories where this all goes down. Okay, Section 1, where magma is born. Now, here's a common misconception, that the Earth's mantle is just this giant ocean of liquid rock. But actually, it's almost entirely solid. Yeah, solid. So it takes some very specific, special conditions to get that solid rock to melt and form magma in the first place. So, how in the world do you melt a planet's mantle? Well, there are 3 main ways to do it. First up, you've got decompression melting. Basically, you take super hot rock that's under immense pressure, and if you just reduce that pressure, it can expand, and boom, it melts. That's exactly what happens where tectonic plates are pulling apart. Then, there's flux melting. Think of this like adding salt to ice to make it melt. In this case, water gets forced into the hot mantle rock, and that lowers its melting temperature, letting it turn into liquid. And finally, the most obvious way, just simple heat transfer. If you pump a batch of really hot magma into some cooler crust, it can literally cook the rock around it until that melts too. Okay, so once that rock melts, the magma that's created isn't all the same stuff. Not at all. It actually belongs to these distinct families, and each one has its own unique personality. So let's meet these main magma families, because as you're about to see, not all magma is created equal. What's so fascinating here is how one single ingredient, silica, pretty much controls everything. Basaltic magma, which is low in silica, is really fluid and runny, kind of like hot syrup. But rhyolitic magma, which is packed with silica, is incredibly thick, almost like a paste. And why is that? Well, the silica molecules link up and form these long chains, and that makes the magma super sticky and resistant to flowing. And this difference in stickiness, or viscosity, it's just staggering. We're talking a difference of up to 6 orders of magnitude. It's that crazy high viscosity that traps gases and leads to those violent explosive eruptions. But a magma's initial chemistry, that's just the beginning of the story. Its recipe is constantly changing as it moves. And one of the most important ways it evolves is through this process called fractional crystallization, which is a really cool story in itself. So let's picture a magma chamber, deep underground. When it starts out, it's a more or less uniform liquid, right? A well-mixed, molten soup of different elements. But as that chamber starts to cool down, it doesn't just freeze solid all at once. Certain minerals that have really high melting points, we're talking things like olivine and pyroxene that are rich in iron and magnesium, they start to crystallize first. And because these brand new crystals are denser than the liquid magma around them, they start to sink to the bottom. And here is the absolute key. By physically removing those early forming crystals, the chemistry of the magma that's left over changes. It's now been robbed of the iron and magnesium that sank to the bottom. That means the leftover melt becomes richer and richer in other elements, like silica. This one process is a huge reason why we can get a whole bunch of different rock types from just one original batch of magma. All right, let's get to the final stage of this whole journey. Eventually, all magma cools and becomes solid rock. But the speed at which it cools is the absolute key factor that determines the final texture we can actually see and feel. And that cooling speed really leads to 2 main types of rock. If magma cools slowly, deep inside the crust, it forms what we call an intrusive rock. This slow cooling gives the mineral crystals plenty of time to grow large enough for us to see with our own eyes, like in a granite countertop. But if that same magma erupts as lava and quickly on the surface, it forms an extrusive rock. The super fast cooling just freezes the atoms right where they are, creating tiny microscopic crystals and a very fine-grained texture, like you see in basalt. So where is all this action happening? Well, it's not random. These processes are concentrated in what you can think of as Earth's great rock factories. And the engine that's driving all of them? Plate tectonics. So the biggest rock factory on the entire planet is the Mid-Ocean Ridge System. This is a gigantic underwater mountain chain where tectonic plates are literally pulling apart. As they separate, hot mantle rock rises up, undergoes that decompression melting we talked about, and just churns out unbelievable volumes of basaltic magma. This process creates what's called mid-ocean ridge basalt, or MORB for short, and it is the single most abundant rock on the surface of our planet. It forms the foundation of all the world's oceans. Now, in total contrast, you've got convergent boundaries, where plates collide. Here, an oceanic plate gets forced down or subducted into the mantle. As it goes deeper, it heats up and releases all of its trapped water. This water then rises into the hot mantle above it. It triggers flux melting and generates those stickier, more gas-rich magmas that feed the explosive chains of volcanoes we see in places like the Andes or the famous Ring of Fire. So the next time you see an igneous rock, just remember the incredible journey it represents. It all started with the very specific conditions that first melted solid rock in the mantle. Its chemical recipe was then totally transformed on its way up, as new crystals formed and separated out. And the texture that you can actually feel was set in its final moments, all depending on whether it cooled slowly underground or super fast on the surface. And this whole thing, the melting, the evolution, the cooling, it's all happening inside these giant geological factories that are driven by plate tectonics. And that leaves us with a final thought. You know, the rocks right beneath our feet, they aren't just static objects. They're a snapshot in time, a record of a dynamic, constantly changing planet. And since this whole rock cycle is a continuous process, it really makes you wonder, doesn't it? What new kinds of rock will Earth's geologic engine create in the next 100 million years? And what incredible stories will they have to tell?